Hi, this is Mr. Barron, and what I want to be doing is podcasting a couple of problems from Chapter 5 dealing with heats of formation and Hess's Law. The first problem that I'm going to be solving for you is problem number 70 from Chapter 5, which is 5.770. Now, if we look at question 70, it tells us that a cigarette lighter contains liquid butane. I'm going to go ahead and write out that formula. So butane is C4H10. And then it says, using the enthalpies of formation, calculate the quantity of heat produced when 1 gram of butane is completely combusted in air. So I know combustion is a reaction with oxygen, and this time it actually does matter what states of matter we write. And the reason is because when you deal with enthalpies of formation, when you look in that table in the back of the book, which is an Appendix C for enthalpies of formation, you'll notice that it does make a difference when you're talking about water, whether it's positive or negative, and it also makes a difference whether we're talking gas or whether we're talking liquid for certain substances. So it's a combustion reaction, which means it's reacting with oxygen gas, and it's going to produce carbon dioxide gas and liquid water, H2O. Okay, now I have to make sure my equation is balanced. So to completely balance my equation, let me start off here. I notice that my carbons are at 4, so I should probably have my carbons 4 here. And then I notice my hydrogens are 10 on this side, so I need this to be 10, so I'm going to put a 5 here. And now I need to make sure my oxygens are balanced. So I look at my oxygens, and I see I have 2 on the left, and I have a total of 8 plus 5, and that's 13. So I need to have 13 over here. An easy, quick way to balance your chemical equation is to do this. Because I have 2 oxygens, if I multiply it by 13 halves, I have 13. And sure enough, if you look at the equation, it is completely balanced. Another way to have written it out is if you really want to get rid of that 2, you could multiply everything by 2, and then you would end up with 2C4H10 plus 13 O2, producing 8 CO2 and 10 H2O. I'm going to write out that 1 very well. Or you could have kept it as what I originally had, which was C4H10 plus 13 halves O2, producing 4 CO2 and 5 H2O. Either of which would work. I'm going to actually go with the second one as opposed to the first one, but you could have done the first one just as well. All right, now what I'm going to do is I'm going to start setting up and solving for all the different formations of everything in my equation. Now remember, oxygen doesn't have a heat of formation, so we can just ignore that when we write out these additional equations. So the first thing I notice is that the C4H10 has to break apart. Hang on a second, let me zoom in so that you guys can see what I'm about to write a tad better. Alright, so I know that this C4H10 has to break apart, so I'm going to write it out like C4H10. And then it breaks apart into its components, which is carbon and hydrogen. So that's C plus H, and I know that hydrogen is part of the Hofbrinkel, so I'm going to write a 2 right there. And then, of course, I have to make sure that this is balanced. So I have 4 carbons, so I need to have 4 carbons on this side, and I have 10 hydrogens there, so I need to have a 5 there. So I go into the back of the book, and in the back of the book in Appendix C, I see that butane, when it's formed, has an enthalpy of formation of negative 147.6. Go in the back and make on the back of the book and check to see if you see the same thing. So if the formation is negative 147.6 kilojoules per mole, then the breaking apart, the decomposition, has got to be the opposite sign, which is positive 147.6 kilojoules per mole. I put that positive there because it's breaking apart, not being formed. Okay, now I'm going to continue on, and then I have to make sure that this number is multiplied by the number of moles of where I got that number from. So the number is representing this, the C4H10. There's no coefficient in front of it, which means it's 1, so I don't need to multiply this number by anything else. Okay, now let's look at CO2. Well, the formation of CO2, notice I am keeping this 4, I'm bringing it down here, is going to be formed by C carbon plus oxygen. Remember, oxygen is part of Hofbrinkel, so I have to have a 2. Make sure the equation's balanced, so I need a 4 in front of here, and then I need a 4 in front of there. So to make sure I have the same number of carbons and oxygens. All right, I look in the back of the book, and the heat of formation for carbon dioxide is negative 393.5 kilojoules per mole. Again, this comes from Appendix C. This time, though, I do have a coefficient in front of what I'm describing the formation of, and that's carbon dioxide. I have a 4 in front of it, so I want to make sure that I multiply this by 4. All right, continuing on. Now I have to write it out for the water. So for the water, I'm producing 5 moles of water, H2O. So what makes up H2O? That's, of course, hydrogen, H2 plus oxygen. I made these both 2 because of Hofbrinkel. I have to balance it, of course, so I'm going to put a 5 in front of this, and then I'm going to put a 5/2 in front of the oxygen just to make sure that it's balanced, because this should give me a total of 5 oxygens, and this should give me a total of 10 hydrogens. Okay, good. Now I'll look up the number in the back of the book. In the back of the book, the heat of formation is negative 285.83 kilojoules per mole. I look at the number of moles, and it's 5, so I'm going to multiply this by 5. All right, so now to find the delta H for the whole thing, I'm going to have to add all 3 of these together. So I'm going to take 147.6 plus the 4 times the negative 393.5 plus the 5 times the negative 285.83. Okay, and of course our answer is going to be in kilojoules per mole once we add all of these together. I add all of them together, and I get negative 2855.6 kilojoules per mole. But the question's asking, well, what happens if you burn a gram of butane? How much energy is released for delta H? So 1 gram of butane's 1 gram C4H10. I have to change this into moles, so I'm going to divide it by the molar mass, or you could write it out in my format, which is the times the conversion factor. And the molar mass is 58.26 grams. So it's going to be 1 divided by 58.26, and that gives me an answer of 0.017 moles of butane, and that's how much was actually burning. Well, I have this number, and I have this number. I'm going to have to obviously multiply the two. The moles are going to go away, and I'm left with kilojoules, which is going to tell me how much heat was released in this chemical reaction. So I'm just going to do this in my calculator. So I'm going to enter in the negative 2855.6 times the moles of butane that are burned, and I'm left with the correct answer, which is delta H is negative 48 kilojoules. If you want to keep it to 3 sig figs, it would be negative 48.5.